Well, greetings, mathletes. Welcome back. Um, so this week's lecture is actually an extension of last week's lecture. I had to think about some things I would have included in last week's lecture, but your book presents things in a way that it made me question them a little bit. Basically, what's happened is, okay, so there's a formula in your book for the standard deviation, and that's what we're going to be talking about today. Um, it's not the usual representation of that formula. There's actually two formulas. And what it does is it uses one formula, but it has the symbols from the other formula. So it was kind of bothering me. But this formula will still be okay. Technically what it is it's the formula for a standard deviation for a population. That's what your book gives you. But then it uses all the symbols for the standard deviation from a sample. It's still going to be useful to us. And since this is, we're not going to be basing any serious statistics on it, I think it'll be okay to go through and just handle it the way that your book handles it. So um, I'm going to go ahead and present the standard deviation here. So we need to have, first of all, a data set. So we're looking at the standard deviation. Okay, so we need a data set, so I'm going to go ahead and start with that. We'll start with x is equal to, let's see, 10, 12, 15, 18, and 20. Pretty much any other data set bigger than 5 points is just going to get really messy. So this is more about understanding what the procedure is. So we have all these x values here. And you can think of the x values as, x1, x2, x3, right, just with subscripts on them. So in general, when we want to find the standard deviation, S, this is how the formula works. We are going to add up the squares of the differences between each individual data value and this will go all the way to xn. Try it again. There we go. All the way up to xn. So the last one would be xn minus x bar squared. And the whole thing, and actually I want to do it this way. I was going to give you the complete formula, but I want to do it in pieces here. And this whole business here, once we add all these things up squared, we're going to divide it by the size of the sample that we're dealing with, or the population. So here's the thing. This is usually not how this stuff is written. And this actually isn't the standard deviation yet. This is what we call the variance. Okay, now your book uses the symbol V for variance. As far as I know, your book is the only place that uses V for variance. What is typically used for variance is S squared. And the reason for it, you notice that's a standard deviation squared. The reason for it is because the standard deviation itself is the square root of the variance. So it's the square root of all this business. Right? So it's all of that over n. And you can see the relationship here. If I take the square root of this, that gives me this. But the same thing is true here. If I take the square root of s squared, I get s. Right? So the symbol is supposed to just tell you how to work between the two. In any case, the variance and the standard deviation, we're really going to be focusing more on the standard deviation. If you take a statistics course, you will include the variance as well, because there's things that you do with the variance. So you can see this is a really messy formula, and it would, if you had more than 5 data points, that numerator would just it would just be painful to deal with. To write that whole thing out, you probably wouldn't even be able to get it on one line. And you think about it, people do this with data sets with, 5,000 data points in it really easy. So there's got to be a better way to organize this, and there will be. So I'm going to assume you have this written down now. And what we're going to do is I'm going to show you a little bit nicer way to get a hold of this. Let's do it this way. Okay, so the nicer way to get a hold of this is to make a table, right? I like to list my values this way. So we have 10, 12, 15. Ooh, my handwriting. 15, 18, and 20, right? So we're looking at that. Now, remember what we were doing in that formula. In fact, let me write the whole thing down here so we can see it. Is that going to leave me room? Right, we got to take all those x1s minus x bars, and I'm just going to shorten this whole thing all the way up to the end. Right, and we got to square all those. Then we have to divide it by n. Then we have to take the square root. So it's really that numerator that's going to be messy. So we're going to use a table to get a hold of this numerator. So I have all my x values, and now I need to see what x minus x bar looks like. Okay, well, x bar is our mean. So that means we have to average these things. So add, 10 plus 12 plus 15 plus 18 plus 20 should give us 75, right? And 75 divided by 5 gives us that our x bar is equal to 15. Right, so that's actually kind of nice. We have 15 right there. So this is 10 minus 15, so that gives me negative 5. 12 minus 15 is negative 3. 15 minus 15 is 0. 18 minus 15 is positive 3. And 20 minus 15 is positive 5. Okay, so that's all the inside pieces, the x minus x bars, all those guys. Now, if you notice, I have to square each one of them as well. So that's going to be my next column. Now, a lot of this you can do in your head as you go, like I'm doing right now. But if the numbers start getting ugly, if you start getting decimals and fractions and stuff like that, it's really best to use a calculator as you go through here. I picked these numbers so that we could keep it small enough to do it in our head. Okay, so now we have the x minus x bars. Now we need to square each one of them. Negative 5 times negative 5 is positive 25. Negative 3 squared is 9, so that gives us 0, 9, 25 again. Okay, so we have all the differences. We've squared all the differences, and if we look at our formula, the next thing would be to add all of them up, right? So that means we need to total these things. We need a sum. So let's add them. 25 and 25 is 50. 18 or 9 and 9 is 18. 50 plus 18 is 68. Right? So far, so good. Okay. So what that means for our formula, what we just got was this whole numerator. So if I want S now, 68, all this stuff up here on top is now 68. So we have 68. N is 5. Right, and so we'd want to do that division, and it's going to come out to, let's see here, that goes in 13, 3 left over, so it's 13.6 is our standard deviation, right? And you can check that. In fact, I should probably check that. 68 divided by 5. It can't be, can it be? Yeah, it's 13.6. Okay, so we win. All right, so we get 13.6 for the standard deviation. And so let me just kind of walk through the process again. So the first thing we want to do is get these inside pieces, right? All these guys in here. this, and all the way up to the last one, which means we need to find the mean first. So you got to find x bar. You subtract each data point from x bar. That gives us all the numbers in this column, and that's basically all the individual terms here. Then we square each of those differences, and we add all those numbers up. Right? You notice by squaring it, you make all those differences positive, because anything you square turns positive. So that gives us a positive distance. It really is a distance. And then once we have that and we add everybody up, we just divide by the number of data points we have. Right? And so we got 13.6. Now at this point, as far as doing things with the standard deviation, we're not going to have a whole lot of application. Right now, it's just basically, can you calculate a standard deviation? So that's what I'm going to be expecting from you. Now, the way this gets used, I was thinking about different ways this might get used, and I thought grades would be a good way to talk about this, because one of the things students always do, and not every student does it, but every class has a student who asks, are we going to curve the grades? I just wanted to show you guys what a real grade curve means, and it's based on the standard deviation, and it's also based on the normal distribution, right? So when it comes to the normal distribution, I want a different color. When it comes to the normal distribution, it's this kind of a curve here, and we talked about this again. Whoa. Let me try that again. There. Yeah, that's not too bad. Okay. The normal distribution basically is determined by its middle, and the middle actually ends up being your mean, right? And then from the middle, what happens is you measure off standard deviations. So remember, S is the symbol for a standard deviation. So if I travel one standard deviation in each direction, right, this is 1S, that's actually significant. And then if I travel 2 standard deviations in each direction, these amounts are also significant. This is 2 standard deviations. And then a third. If I travel a third standard deviation out here, that also ends up being significant. And then anything past that, we're not going to worry about that right now. But certainly there are stuff that goes past this. Now, this is based on something called the empirical rule. The empirical rule basically gives you a rule of thumb for how much area is under these curves in terms of the standard deviations. So the first area I want to look at is this area here, right? It's probably, yeah, I'll do that. Right? So it's that middle area, everything within one standard deviation. Okay, the empirical rule says if you have stuff within one standard deviation, this is 68% of your data, right? If your population is normally distributed, whatever property you're measuring, grades are normally distributed typically, if you look at the percentages. And so you tend to have a lot of C's, fewer B's, very few A's. Same thing in the reverse. If you have a lot of C's, a few less D's, and even fewer F's. That's generally the idea. But let's go ahead and take a look here a little further. So 68% of our data lies within one standard deviation. If I take it further, if I go to the next one, to 2 standard deviations, right? It turns out 95% of the data falls within 2 standard deviations. And if you go to 3 standard deviations, 99.8% of the data falls within 3 standard deviations. And then this very last end, if you start doing the arithmetic, these two ends are 0.1%. Okay, now if we break things up a little bit smaller and start looking at how much area is in these smaller pieces, like, how much is in here with the 2 standard deviations. And you can work it out because this is the area on the left is the same as the area on the right. You already have 68% of your data, right? And so if you already have 68% of your data here, you can start teasing out what's left over. So you have 68% in the middle. I should write that in red just to match up. That is an eraser. Let's try this again. So 68% here in the middle. Now, in the next gap here, you have 13.5%. In this little gap, this between 2 and 3 standard deviations out there, you have 2.4%. Let me switch colors one more time so we can keep this coded. So this area in here is 2.4%. Right? Now, what's kind of nice about this is most of the time you don't worry about this. You just take the whole thing and include this other 0.1, right? Because if you put these two together, you get 2.5%. And that's typically what people do. Same thing over on this end. We can say, okay, that's 2.5%. So these two tails here actually comprise 5% of the curve. Okay, so here's how grades are affected by this. If your teacher, professor, tutor, whatever, decides to put grades on a curve, a true curve, most people, they just want their grade adjusted. Are you going to add 5 points to everybody? That's not what a curve is. A curve says, we're going to take the class and divide it up by these percentages, right? So everyone within 1 standard deviation of average gets a C. Everyone above 1 standard deviation but less than 2 standard deviation gets a B. And then the top 2.5% that's over 3 standard deviation gets an A. On the reverse side, we say that after you cross 1 standard deviation, between 2 and 3 standard deviations below average is a D, and below 2 standard deviations is an F, right? So basically, you want to stay within 2 standard deviations, right? So let's look at how that plays out. This is where it gets kind of unfortunate for students when you actually do this. Okay, so I want to look at it this way. So we'll have a grade, we'll have a percentage, and then the number of students. Right? So it ends up being boiled down this way. The guys down here at the end are A's. So we get A's here, B's here, C's for this whole middle region, D's here, and F's here. Right? That's basically how it boils down. In fact, it might look a little bit nicer if I just get this off of here. Okay, so if we look at, let's just do this. Since I got everything off there anyways. So these are F's, these are D's, this whole middle thing is C's, and then you get B's and A's. And it doesn't seem so bad. So let's take a look. We got A, B, C, D, F. And just for the sake of computation, I'm going to make this a huge class. I'm going to say that n equals 200. So n equals 200. Okay, so the number of people with A's, if we look down here, well, we have 2.5%. B's, I have 13.5%. C's, I have 68%. D's, 13.5%. And F's, 2.5%. So far, it doesn't seem so bad. But if I take 2.5% of 200, that means I'm just to remind you guys, if I want to take that percentage, it's 0.025 times 200. What you end up with is 5. Here you get 27. I think that's what, 136? Yeah, 136. And then again, we have 13.5%, which ends up being 27. And then down here, 5%. So it doesn't look terrible. I mean, looking at this, not 5%, 5 students. There we go. We look at this, only 5 students got F's. But at the same time, only 5 students got A's. So out of these 200 students, this is how this ends up playing out. All the scores get listed, right? So you have all these different scores here, and there's 200 of them. And you list them in order from largest to smallest. The first 5 get A's, period. Doesn't matter what the score is. That's why I just wrote pound signs. The first 5 get A's no matter what. The next 27 get A's or get B's no matter what. The next 136 get C's. So that's a huge chunk of the class. 136 students out of 200 students get C's, 27 D's, and only 5 F's. That sounds great. But, and here's where the kicker comes in. It doesn't matter what the scores are. Suppose the lowest score in class was at 85%. Under normal circumstances, that's a B, right? If that was the lowest score in the class, if I'm deciding grades on a curve, that's an F, right? So a true curve doesn't look at the percentages. It doesn't look at what your actual score is. It looks at the position of your score when you list everybody in class. And so if you list them from smallest to biggest, right? These guys are A's, these guys are B's. You would just divvy it up. There's no, you don't have to do any heavier calculation. So it makes it real easy to decide grades for professors or for teachers. But it's not so great for students, especially if you have a competitive class. This is part of the reason they do this in medical schools and stuff, is because they want everyone competing against everyone else. It's a situation where if you're going to be cutting people open and stuff, you want the best of the best doing that. And so you make them all compete against each other to be able to do it. Right? And that's really the idea. So in any case, that pretty much wraps up what I wanted to talk about today. So I'm going to go ahead and kill that. And yeah. So again, if you have any questions, make sure to contact me. And until next time, keep your pencils and your wits sharp.